All right, so now that we know how to do or assign oxidation numbers, we can use those to figure out what is being oxidized and what's being reduced in a chemical reaction. Um, and so we're gonna use those, or the first step in determining that is going to be using those or assigning those oxidation numbers for every atom in every compound on both sides of the chemical equation. All right, and then secondly, we're going to take a look at those oxidation numbers, and we are going to try to determine, or we're going to determine, what oxidation numbers change from the reactant to the product side of the chemical equation. Um, for me, this is one of my favorite things to do in chemistry. I love looking at redox, which is one of the reasons why I said we should go back and look at it again. But also, it gives us a good segue into a very very brief discussion of electrochemistry. So the equation that we were looking at before is this reaction of chlorine gas with copper, and we said the chlorine gas was reduced to produce chloride ion, and the copper was oxidized to produce copper 2 ion. And you know what what we need to do to determine that, or what I did to determine that, was I figured out what the oxidation numbers were of each of the elements in each of the compounds, and then decided or determined which ones changed. It really is that straightforward. Now, before we go any further, I want to note that the stoichiometric coefficients in front of all those different things in that balanced chemical equation up there has nothing to do with the oxidation number. So just because there's a 2 in front of the chloride ion there, the chloride ion's oxidation number is still going to be -1. That 2, it matters in a lot of different things in chemistry, but in redox, the coefficient doesn't matter at all. And it turns out those coefficients come from the number of electrons that are transferred, and that comes into balancing redox reactions, and we're going to see how to do that coming up soon. Um, but note that the stoichiometric coefficients have nothing to do or no bearing on what the oxidation number will be. So if we're looking at this, we're going to look at chlorine gas. Chlorine gas's oxidation, its oxidation number is going to be 0, and it's going to be 0 because it's in its elemental state. So Cl2, it's one of those elements that, or one of those 7 elements that exists as a diatomic. So we look at that and we say, okay, it's an element by itself, elemental state. And I'm going to just move directly to the right. I'm going to say copper. Okay, copper is an atom sitting there by itself. Atom by itself, elemental state, oxidation number of 0, or oxidation state of 0. Move to the right, now we're into the products. Chloride ion, Cl minus, monatomic ion. Charge is the oxidation number. So for chloride ion, the oxidation number is -1. And then copper, another monatomic ion, has a charge of +2. So its oxidation number is going to be +2. So we've gone through and we've assigned an oxidation number to every atom that's in that chemical equation. So the way I like to write these out is I just like to write the oxidation number either above or below the elements. Here you can see they're below just because I think it's a little bit easier. Sometimes I'll do them above, so if you see my homework keys or something like that, you may see them that way. But they're all indicated here. And now I'm just going to look and I'm going to say, okay, what's a chlorine atom on the left-hand side, and what is its oxidation number on the right-hand side? And it goes from a 0 to a -1. Or if we look at copper, copper goes from a 0 to a +2. So we see that there are changes in oxidation number as we go from the reactant to the product side, looking at the same atom or the same type of atom. Okay, so copper goes from a 0 to a +2. Whenever oxidation number increases or gets larger, that means it's an oxidation process. So copper must be losing 2 electrons here. It's oxidized. It goes from a 0 to a +2. Then we have chlorine goes from a 0. Chlorine gas goes from a 0 to a -1. Its oxidation number gets smaller or more negative. And so we would say that chlorine is gaining electrons, or it's being reduced. Its oxidation number is going from a 0 to a -1. So we know now what's oxidized, the copper, and what's reduced, the chlorine. We know that from the oxidation number. The only thing left is to decipher or determine what's an oxidizing agent, what's a reducing agent. So copper is a reducing agent because it's being oxidized. So whatever is oxidized is a reducing agent. It's the reducing agent because it's causing chlorine to be reduced. Chlorine's being reduced. That means it must be the oxidizing agent. It's the oxidizing agent because it's causing copper to be oxidized. So that's how we use the oxidation number to figure out, all right, what's being oxidized and what's being reduced. So now let's take a look at another example. So magnesium plus hydrochloric acid. I believe that we saw this in Chemistry 110 laboratory, if you were in Chemistry 110, in that I think we determined the hydrogen gas, the volume of hydrogen gas that was coming off to determine the atomic weight of a metal. It's where you collect it under a bucket in a graduated cylinder or a beaker. I just can't remember now off the top of my head. Had too many days in the basement, I guess. So what I want you to do here is I want you to take a look at this particular reaction, which is a redox reaction. Okay, if there's no redox reaction, you won't see any change in oxidation number for atoms as they go from the reactant to the product side, but in this case there will be one. But what I want you to do is try to assign the oxidation numbers for each of those elements in each of those compounds. So maybe pause the video right here, take a couple seconds, write down the equation, assign the oxidation numbers, and then unpause it and see if you got it right. So if you look here, the magnesium's in its elemental state. Oxidation number is 0. Hydrogen in a compound is +1. Chlorine then must be a -1 to balance that +1 because HCl, or hydrochloric acid, has a charge of 0. Magnesium chloride on the other side is an ionic compound. Ionic compound, if you know what the charge of the ions would be, you know what their oxidation number would be. Magnesium's a +2 ion in magnesium chloride, so it's going to have an oxidation number of +2. Chloride ion has a charge of -1, so it's going to have an oxidation number of -1. And then hydrogen is in its elemental state there on the far right. So we've gotten all of the oxidation numbers assigned. Now let's look. Okay, magnesium on the left-hand side is 0. And magnesium on the right-hand side is +2. So its oxidation number, magnesium's oxidation number is changing. All right, it's going from a 0 to a +2. And then I look and I say, okay, chlorine on the left is -1, chlorine on the right is -1, it doesn't change. But hydrogen on the left is +1 and it's 0 on the right-hand side, so it's changing too. So we have two things that are changing. All right, so do any of the elements change? Yes. Magnesium goes from a 0 to a +2. Its oxidation number is getting larger, getting more positive. So it's the oxidation process. Magnesium is going from a 0 to a +2, means it's oxidized. If it's oxidized, it must be reducing something else, so it's the reducing agent. What is it reducing? It's reducing the hydrochloric acid, the HCl. And it's the hydrogen atom inside of there that's being reduced, but we normally would say that hydrochloric acid is being reduced. How do I know it's being reduced? It's because its oxidation number is going from a +1 to a 0. It's getting smaller, getting more negative. And so we would say that the hydrogen in the hydrochloric acid is going from a +1 to a 0, but we would say that hydrochloric acid is being reduced, HCl. All right? Since hydrochloric acid is being reduced, it must be oxidizing something else, so it's the oxidizing agent in this particular redox reaction. So now we've got everything that we need. All right, let's try one more example. Iron reacting with nickel nitrate. So again, pause it, determine oxidation numbers, see if you can figure out what's being oxidized and what's reduced, what's the oxidizing and reducing agent. So if we look, the iron goes from is a 0. Why? Because it's elemental state. And right away I like to scan the whole equation and I see nickel on the far right hand side. Again, elemental state. How do I know? Well, it's just an atom sitting there by itself. When an atom's by itself, that's a tip-off with no charge. That's a tip-off that it's got an oxidation number of 0 because it's in its elemental state. The other's not as easy. are not as simple. Okay, so what you're going to want to do is figure out what the charges would be on the nickel and the iron atoms in each of those compounds. The nickel's a +2. How do I know that? Because nitrate's a -1 and there are 2 of them. All right, so in order to cancel out that charge, all right, the nickel must be a +2. Iron, same reasoning on the right-hand side. It's got to be a +2 because in that compound there are 2 nitrate ions, and the nitrate ions each have a -1 charge, and there are 2 of them, so that's a -2 charge total from the nitrate, so the iron's got to be +2 charge. But if you have some other way that you rationalize what the charge of an ion is in an ionic compound, go ahead and go with that. Run with it. That's perfectly fine. Nitrate not as simple. The reason why nitrate's not so simple is because it's not an ionic compound. So you got to go through that whole process of 1 nitrogen plus 3 oxygen add up to equal the charge of the ion in the same way that we determined the oxidation number of nitrate last time. And that doesn't have to be nitrate. It can be almost anything. But know that you will perform the same type of operation or calculation that you did for nitrate whenever we were working on that one in the last video. And so we find that nitrogen's a +5 in nitrate, oxygen's a -2, of course, because we always assume that that oxygen's a -2. And we have nitrate on both sides, so if it's the same on both sides, it's going to have the same oxidation numbers. So, do any of the elements have a change in oxidation number? Well, iron goes from a 0 to a +2. Nitrogen doesn't change, oxygen doesn't change, and nickel goes from a +2 to a 0. So we have 2 things that change. That's perfect. That's what we want. Okay, so iron goes from a 0 to a +2. Its oxidation number is increasing, becoming more positive. So that must be the oxidation process. So iron is going from a 0 to a +2. It's being oxidized. If it's being oxidized, it must be reducing something else. What is it reducing? Well, it must be reducing the nickel nitrate. All right. The nickel in the nickel nitrate is a +2. It goes to a charge of, or an oxidation number of 0 on the right-hand side. Its oxidation number is getting smaller. It's decreasing. So we would call that reduction. So we would say that iron is being oxidized. It's the reducing agent. What is it reducing? It's reducing the nickel 2 nitrate. The nickel 2 nitrate is being reduced. That means it must be oxidizing something else. It's oxidizing the iron. So that's it. That's how you determine oxidizing and reducing agents. We're going to see how you balance a redox equation like that coming in the next video.